In this video, we'll prove that Dijkstra's algorithm is correct. Let's write out a problem statement and a theorem. Have a read. This theorem actually has several parts. The first part claims that the algorithm terminates. If it didn't terminate, it would be a pretty rubbish algorithm and it wouldn't even make sense to ask if its answer is correct. The second claim in the theorem is that the answer is indeed correct. In other words, at termination, we claim that for every vertex, the computed value v.distance is equal to the shortest path distance from S to V. Let me just pause there and reiterate a vitally important point. The thing on the left is a computed value. It's what the algorithm is storing and updating during its execution. The thing on the right is platonic. It comes from a mathematical definition. In the last video, we wrote out a mathematical definition of the distance function. It's the minimum cost of any path from S to V, and that is defined in a way which is independent of any particular algorithm. So this theorem says the value that our algorithm computes is equal to the desired mathematically defined quantity. Now, it may seem like I'm banging on about an obvious point, but I assure you it's not obvious. And every year there are exam answers that get low marks from students who engage in wishful thinking and don't keep straight the difference between what our algorithm does and what we want it to do. Finally, one more part of the theorem. This part claims that the two assertions we wrote down inside the algorithm will never fail. In fact, we'll prove this last bit first, and then once we've proved it, then the rest of the theorem will just drop out easily. So this is the time for you to go back and look at the code and at the two assertions. There isn't room on a video screen to show you code and to have legible writing at the same time, so please make sure you have a printout or some other screen where you can look at the code at the same time as we're going through the proof. Okay, at last we're ready for the maths. Actually, before the maths, let me share another quote from Dijkstra. He said, "Programming is one of the most difficult branches of applied mathematics. The poorer mathematicians had better remain pure mathematicians." The proof that we're about to see will look pretty heavy going, especially because for many of you, you've seen maths proofs for maths problems, but this is perhaps the first time you've seen a maths proof for an algorithm. A proof is not something that you should expect to understand the first time you see it. As you watch this video, take in the rough outline of the proof. But to really understand what's going on, you really have to write out the proof for yourself. And you need to write it on a large piece of paper so you can see all the reasoning in a glance. But still, the hardest part of proving a maths theorem is the bit that we've already just done, which is writing out a properly stated theorem. The most important thing to know is where we're heading, the rest is just hard work. Okay, so now we can get started. We're going to start with the two assertions. Let's first prove assertion 9, which says that just after a vertex v is popped, then its computed value, v.distance, is equal to the platonic mathematical quantity, the shortest distance from S to V. The assertion isn't claiming that this equation holds at all points in time, it's just claiming that it's true at this particular instant in time, just after v is popped. We're going to prove it by contradiction. Let's suppose the assertion fails, and it may fail one or more times during the execution of the algorithm. And let's consider the very first point in time during an execution at which it failed. For the sake of definiteness, let's introduce some terminology here. Let v be the vertex on which it first fails, and let t be the first time instant that it fails. Doesn't really matter how we measure t, I just want to be able to refer to before t and after t. Okay, so the assertion failed for vertex v. There exists some shortest path to v, let's call it u1 up to uk, where the first vertex u1 is s and the last vertex uk is v. And by this I mean shortest path in the platonic mathematical sense, the path that God knows about. I do not mean the path that our algorithm has learnt about so far. Now, I want to think about the state of all the vertices on this path at point in time during execution t. Either all of these vertices have been popped by time t, or they haven't. So there are two possible cases for us to consider here, case 1 and case 2. Let's consider case 1 first. We know we've popped v and we popped s right at the beginning, and so somewhere in between there's a vertex that hasn't yet been popped by time t. Let's focus on the first vertex in this sequence that hasn't yet been popped and let it be ui. In other words, vertices u1 up to ui minus 1 have all been popped prior to time t, ui hasn't been popped, and then there are one or more vertices going up to uk which may or may not have been popped. I'm not fussed about them. Next, here are some lines of maths that are the real heart of the proof. Here they are. I've written them all out and we're going to go through them step by step. The first step says that the distance from S to V is less than V dot distance. Why is this true? Well, we're talking about the state of the algorithm at time t, and we know that the assertion just failed. Therefore, V dot distance is not equal to the true mathematical distance from S to V. Now, could V dot distance possibly be smaller? No, it can't, because the algorithm will only set V dot distance when it discovers a legitimate path to V. That's what the test inside the inner loop of Dijkstra's algorithm ensures. Okay, so we know V dot distance is incorrect. There's no way it can be smaller than the correct value, therefore it must be larger. The second step is to say V dot distance is less than or equal to ui dot distance. This step relies on the priority queue mechanism, which is the distinctive cunning bit of Dijkstra's algorithm. Let's think about what was in the priority queue. We know V was in there a moment ago because we're stopping the algorithm just after V got popped. Well, and what about ui? We know that ui hasn't yet been popped because that was what we chose I to be. But we also know that ui should be in the queue because ui-1 has previously been popped. And when that happened, we'd have run through all its neighbours, and any that weren't in the queue we would have added them. Okay, so that tells us that both V and ui were in the queue just before time t. They were both candidates for being popped, and the one that we did pop was V. And what priority queues do is they always give us the item with the smallest key, and therefore V's key must be smaller than ui's. In other words, V dot distance is less than or equal to ui dot distance. Okay, next step. I want to say something about how big ui dot distance can possibly be. Let's think about what happened when we popped ui minus 1. At that time, we scanned through all of its neighbours, including ui, and we updated the distance to each of them if necessary. This equation here, relating ui dot distance to ui minus 1 dot distance plus edge cost, is exactly what we used for the update. We said if ui dot distance is bigger, then decrease its key, and if ui dot distance is already smaller, then leave its key unchanged. Okay, so this inequality is definitely true. Or, to be precise, it was true when we ran through ui minus 1's neighbours, which was some time ago. We need to ask, could anything have happened since then to mess up the inequality? Well, ui dot distance could certainly have decreased in the meantime, but that would leave the inequality still true. It can't have increased in the meantime because Dijkstra's algorithm has this ratchet mechanism, the test on line 13, which ensures that ui dot distance will never increase. And what about the right hand side? Could ui minus 1 dot distance have decreased between when it was popped and now at time t? No, it can't. We know that ui minus 1 dot distance was correct when it was popped. In other words, it was equal to the shortest path distance from S to ui minus 1. That's what the assertion says, and we know the assertion didn't fail on ui minus 1 because we've said V is the first vertex at which it fails. So the assertion must have been true back then when ui-1 got popped. And if the assertion was true back then there's no possible shorter path to ui-1. And remember, the algorithm only updates ui-1.distance when it finds a shorter path. Therefore, ui-1.distance can't have changed since it was popped. Okay, next step. This one's easier. This is just a repeat of what we said for the last line. We said ui-1.distance was correct when it was popped, and we also said it can't have changed since then. So ui-1.distance is still equal to the true shortest path distance from S to ui-1. And finally, the last inequality. There's nothing computational in this inequality, it's purely a statement about Platonic mathematical distances. To see where this inequality comes from, look back at the shortest path we're considering. We said, let u1, u2, ... uk be a shortest path from S to V. In other words, the distance from S to V is equal to the sum of the edge costs along this path. Along this path, we've certainly got the edge ui-1 to ui. Then we've got some extra edges. So if I can just prove that the distance from S to ui-1 is equal to the sum of the first set of edges, then the inequality will be proved. Okay, so what is the distance from S to ui-1? Could it possibly be shorter than the sum of these edges up to ui-1? No, it can't, because if we could find a shorter path to ui-1, we could just swap it into this path here, and that would give us a shorter path to V, but we define this path to be a shortest path. Okay, so that proves this inequality. Good. Let's summarize what all this algebra has proved. We started out with distance from S to V, and we proved that it's less than something, which is less than or equal to something else, ... less than or equal to distance from S to V. In other words, we have proved distance from S to V is strictly less than the distance from S to V. That's a contradiction, so our premise is false. And what are our premises here? We assumed firstly that the assertion failed. Secondly, we assumed that case 1 happened. One or other of these premises must be false. Either the assertion on line 9 never fails, or it did fail and case 1 didn't happen. Okay, let's look at the second possibility. Let's look now at the scenario where case 1 didn't happen. We'll look at case 2, the case where all the vertices on the path from u1 up to uk have been popped by time t. There's some very similar reasoning here, just a bit simpler than before, and I won't go through it all. What it leads to, again, is a contradiction. So, let's summarize. We supposed that the assertion on line 9 failed. We showed that this supposition leads to a contradiction. Therefore, we conclude the supposition is false, i.e., our assertion never fails, and this ends our proof. Okay, that was quite a lot of heavy reasoning, but it's also a beautiful piece of thinking. Nearly every step in our proof corresponded to some line of code in the algorithm. We brought in the nature of the priority queue, the clause in the algorithm that decides whether or not to update, and the definition of shortest path. That's when you can tell you have a really top-notch piece of code, when every line of it is a vital ingredient in a proof of correctness. Before we go on to prove the other assertion and to finish the proof, I just want to recap what we've done here in this proof. What we've used is what you might call a breakpoint proof strategy. We first of all invented a useful property that we would like to be true at all points during execution. In this case, a property about the computed to distance values. We assumed it was true up until some point in time t-1, and then we reasoned about what could possibly happen next and proved that it must therefore be true at time t. In our case, we did this proof by contradiction. I like to think of this as a breakpoint type proof. Imagine setting a breakpoint at some line in your code. We stop the execution at that point, and we look at all the variables and all the data structures, and we reason about what must happen next. Or, if you think like a mathematician rather than a programmer, you'll recognize this as a proof by induction. In any proof by induction, you have an ordered sequence of statements, and you have an induction step saying if statement n is true, then statement n plus 1 is true. A breakpoint proof is proof by induction using the ordering given by algorithm execution time. To be strict about this, in any proof by induction, we also need a base case. Here the base case is my assertion didn't fail at vertex S, i.e. on the first pass through. It would take some pretty messed up code to fail at the very first instant, and the algorithm doesn't do that. Okay, let's get back to the rest of the proof. We've proved that the assertion on line 9 never fails. Next, what about the assertion on line 10? This assertion claims that a vertex v, once it's been popped, is never put back into the priority queue. This is much easier to prove, and really it's just reiterating ideas that we've already seen from the last proof. The proof is just made up of two observations. First, looking at the code on line 13, we see that vertex w can only be pushed into the priority queue when we discover a path that's shorter than the stored w.distance. But when we popped v, we just proved the assertion on line 9, namely that v.distance is equal to the true shortest path distance. So there can't be any shorter path than what we've already found. Therefore, v will never be pushed back. Great, that was easy. Now, just a final bit of wrapping up to prove the two main claims of the theorem. Let's remind ourselves what they were. The theorem claims, first, that the algorithm will terminate. Second, that when it terminates, all the computed distances are equal to the true shortest path distances. First, termination. The assertion on line 10 tells us about termination. It says that a vertex once popped will never be pushed back. So we pop each vertex at most once, so the algorithm must terminate. Next, correctness. In other words, does the algorithm give the correct result? At first glance, it looks like we've already proved this. Isn't that what the big assertion on line 9 said, and what we spent all that time proving? Well, not quite. We have so far proved that any vertex at the time it's popped has the correct v.distance. What we also need to say is that, first, every reachable vertex will sooner or later be pushed into the queue and then popped. And if we're being really strict, we should really add in here a comment saying, for the unreachable vertices, they're initialized to have distance equal to infinity, and that distance has never changed, so they're correct also. Second, we need to argue that a vertex, once it gets popped, we need to say that its computed distance won't change from then up until the end of the algorithm. Now, both of these things are fairly simple to argue, and in fact we've made the second argument already as part of our proof of assertion 9. So I'm not going to go through the details. Okay, that was a lot of proof. The thing about maths proofs is that they're a bit like cybersecurity. Just like security experts have to do threat analyses and look at every way that an attacker could possibly hack the system, mathematicians have to argue defensively and deal with every little corner case. It's good to read a proof and skim through it and get the general gist. But to properly appreciate a proof, you have to approach it like an attacker. You have to find all the holes, all the counterexamples that the proof has failed to take account of. We're going to talk more about proofs and misproofs in the next video. But before that, just to wrap up our discussion of Dijkstra's algorithm, I want to go back to a question I posed earlier on in this video. In the problem statement, we said that the algorithm is only meant for graphs where all edge costs are above or equal to 0. What's this restriction for? There are two ways to answer this. First, we could say, what might the algorithm do if some of the costs are negative? Second, we might ask, does the proof rely on costs not being negative? Let's talk about the proof first. Here's the proof again for the assertion on line 9 with both cases written out fully. And if you put on your hacker hat and look for a vulnerability, this is where it is. This step does not work if there are some negative costs. And then, if this step fails, assertion 9 can fail, and then all the rest of the proof unravels. But is this just a weak proof, or is it really a problem with the algorithm? Let's build a concrete example where this inequality fails thanks to negative costs, and see what the algorithm does. We want to be thinking about a case where the total distance from S to V is made smaller because of negative costs. So here's a nice simple example. The true shortest path from S to V goes along the top, and it wins out over the direct S to V edge thanks to that final negative edge cost from X to V. So let's see how the algorithm will play out here. We'll initialize the priority queue to contain only S, then we'll pop it, then we'll pop its nearest neighbor W, and then it has a choice between X at distance 12 or V at distance 10, so it pops V. Now let's do a breakpoint. We'll pause the execution, we'll inspect the state of the data structure. The proof tells us, consider a shortest path from S to V, label the vertices U1 up to UK, and let UI be the first vertex in the sequence that hasn't yet been popped. So UI in the proof is referring to X. And if we just fill out all the values in this train of inequalities, these are the numbers we get. All the inequalities are valid except for the last one, thanks to our negative edge cost. So this is definitely a case where our proof trips up. Let's run it further and see what the consequences are for the algorithm. Next, it will pop X with distance 12, and then it will discover a better path to V via X. It will push V back into the queue, and then it will pop it with distance 7. Okay, so our assertion 9, the one that says when V is popped, its distance is correct, we constructed our example so that assertion 9 failed the first time V was popped. And now we see that assertion 10, the one that says a vertex once popped is never pushed back into the queue, that's failed too. The whole proof is unraveling. Still, this case isn't too bad. Our proof didn't work, but the algorithm did at least discover the correct distances in the end. But what about the other bits of the proof? We proved that the algorithm would always terminate, and our proof relied on the assertion that vertices are never pushed back into the queue. In this example, it did happen to terminate, but our proof doesn't work. Does that mean there are cases where the algorithm doesn't terminate? Can we tweak our example to make it so that V gets pushed back into the queue over and over again? Here's just a tiny tweak to the graph. This extra edge means that once we discover the path to V of length 7, we get a new path to X of length 11, and so we get a new path to V of length 6, and so on, and it repeats indefinitely. So our proof of termination failed, and we've constructed an example where the algorithm fails to terminate. Okay, so that tells us there's something seriously wrong with running Dijkstra's algorithm when costs are allowed to be negative. In the next video, we're going to talk a bit more about proofs and about counterexamples, and after that, we're going to look at a class of shortest path problems where we absolutely do want to have negative costs, and so we'll need to look at a different algorithm that's able to cope with them.